Now I basically want to demonstrate how basically this message passing happens using a concept called basically unfolded subtree pattern of the graph of basically each node. So let's consider this graph, and then next, this node is receiving information in the first iteration of message passing from its neighbors, right? So node 1 is receiving information from its immediate neighbors, nodes 2, 3, and node 6, right? And then in the next iteration, right, it is receiving, so these nodes already received information from their basically neighbors. So 1 in the iteration 2 is receiving information that these guys had from the first iteration from their neighbors. So essentially node 1 is receiving information from its 2 hot neighbors, right? So now we can show this by unfolding this node as the root of a subtree pattern. We can see this node is our node 1. Then we have 3 nodes, 3 immediate basically neighbors for this node, and those are nodes 2, 3, and 6, right? And then each of these nodes have its neighbors of its own, right? So node 2 has node 1 and 3. Node 3 has basically node 6 has nodes 1 and basically 5. And then node 3, for instance, has nodes 2, 1, 5, and 4 as its neighbors, right? So essentially, now we can write this as basically the set of informations that node 1 is receiving. We can basically structure it this way, right? So now 1 in the first iteration, so this is the first iteration, receives information from 2, 3, and 6. The second iteration, it's receiving information from 1 and 3, 1 being its basically hidden activation in the previous iterations. And 3 is receiving basically from these nodes, so on and so forth. So in the second iteration, those information gets to node number 1, right? Now we can repeat this for every node that we have, right? So that's node 1. We can basically consider a second node, node 2 as well. And let's say that this node has 2 neighbors, immediate neighbors, nodes 1 and 3. Node 1 has 2 neighbors of its own, nodes 2, 3, I'm sorry, 3 nodes of its own, 2, 3, and 6, right? And then the other one, the other neighbor of node 2, node 3 has 4 neighbors of its own, nodes 2, 1, 5, and 4. Right. So, and I can repeat that for all the nodes that I have, and I basically can write that down. So in neural message passing, we're propagating these with a set of weights, right? And this set of weights, for instance, we have WK. Let's just consider it as a single basically set of parameters for abbreviation. So let's say that this WK is the weights for basically that collects information from 2, 3, and 6 and passes it to basically so that we update the state of 1. And then in the previous iteration, we had a corresponding weights as well, right? So that's going to be another set of basically parameters, right? So I can continue that, right? So I can basically correspond these weights to different essentially iterations, right? Different iterations have different weights. And I'm sharing this with all the nodes that I have, right? So this time, instead of directly learning basically model parameters for each individual node, I have an algorithm which is using the same set of weights over all the nodes that I have, right? And I'm sharing it throughout this basically graph. So I can take this, write for basically all height 2 subtree pattern root to that different nodes. And then I'm essentially sharing the same weights WK and WK minus 1 for all these essentially nodes, right? So that's one basically problem that we had with shallow embeddings, that they were not sharing information, and I had to have basically V times D basically model parameters. Now, go ahead.
So when I'm updating WK, I'm just looking at WK minus 1, right? I'm not looking at the previous weights, or I'm looking at
WK minus 1 is the previous weight.
just one previous, right? I'm not taking the whole.
I mean, it is just like the back propagation. You're looking at your forward, right? When you back propagate,
Yeah.
for your computation, you're using the nodes in the basically weights in the downstream.
Right. Okay.
For compute, so in the forward, right? Your question is when I'm computing W, not H. If you're computing H, you're looking at the previous weights, right?
Okay.
If you're computing W is initialized with something like every other network, and then in back propagation, you come basically compute derivatives starting from last layer toward that layer, right? So you're using the weights from downstream to compute basically that, right?
Okay.
So now there are various ways to motivate these models. We can basically use a spectral convolutional basically analogy to discuss this, but we haven't really looked at basically signal processing on graphs. So we will basically look at this later. The second type is we can define it as a differentiable loopy belief propagation model. And the third approach is just by some analogy with the classical graph isomorphism tests that we basically looked at earlier in our kernel methods session. And that's what we are actually going to do. We're going to look at the Weisfeiler-Lemon algorithm, right? Which was used for computing basically it was a test to see if two different graphs are isomorphic or not, right? And using that, we're going to motivate our basically basic graph neural network that you're dealing with here. So let's just review the Weisfeiler-Lemon algorithm. So in this algorithm, we had a set of initial labels corresponding to different nodes in the graph. We were essentially initializing our basically nodes with some label 1, right? Every node in our graph. And then iteratively, we went over the neighborhood over each node, and we gathered essentially multi-set of different labels at the neighborhood of each basically node. And so these nodes Vj that are neighbors of Viv collected and constructed a multi-set of their labels. And then we sorted this, right? So that they have basically, they're in order, these numbers. And then the next step, we constructed a tuple using the multi-sets of the basically neighborhood labels and the current label of that node that we are discussing, Vi. So we are representing that with Hi, this label. And then we had some hash function, which was hashing them, relabeling them, meaning that it was essentially associating a new label to every node that we have. And then this new label is going to be our new label for the current node that we're dealing with. And we were continuing this for multiple iterations until, we see basically two different graphs have the same basically number of seeing different labels, right? If the number of the times that different labels were observed in two graphs was the same, the count of them, they are histograms, they basically were isomorphic. Now, we can use this to motivate our problem. We can say that in a graph-based propagation rules, that's basically like a simple graph neural network that we discussed, we can just simply replace the sort function, this multi-set, constructing the multi-set and sorting them, and the hash function with some differentiable functions, and that's going to be equal to the models that we had, right? So here sorting, basically aggregating and sorting labels from our neighborhood is essentially equivalent to the summing function, right? Now in our model, we're summing over different embeddings in our neighborhood, right? And that's gonna construct us a message, right? This message is equal to the neighborhood aggregation information in the multi-file, basically bifilar lemma algorithm. Then we constructed the tuple, right? We are also considering the current state of our embedding in our graph neural network, right? So the next step, what we do is to linearly combining these two. We can linearly combine the embedding here and the messages that we're receiving from neighbors. And that's going to be analog to the hash function, the relabeling that we have. So we have just defined basically differentiable versions of this. And loosely speaking, we can present our propagation rule as a differentiable and parameterized version of the bifilar lemma algorithm. Because you see, we have now two parameters. Apart from this being differentiable, this guy didn't have any parameters, right? It was just sorting, aggregating these neighbors, and it was sorting them. And these embeddings were essentially labels, right? And we were relabeling by hashing, we meant relabeling. Now we have basically, apart from being differential, we also have two sets of parameters that we were learning, right? So it is both differential and basically parameterized versions of this. Right. So I'm gonna now take a quick look at a method to kind of simplify our representation of our equation. And this is the question that you were asking. So we have a graph. Let's say that we have a graph. We can kind of make this equation look kind of nicer, but by introducing self loops into our basically aggregation and adaptation equations. So in the previous model, and basically in the simple graph neural network, what we had was that we had a set of messages from the neighbors, and we had our current state, and we linearly combined these. And we had different sets of weights for the messages and the current state that we have, right? Now we can, instead of having two sets, we can kind of combine them. And we can do that by introducing self loops to each node. That way, each node is a neighbor of itself as well, right? So you have this node, right? This has basically three neighbors. If I add a self loop, an edge that is connecting this node to itself, now this node is the neighbor of itself, right? Now, if I want to apply that function basically in the matrix form, now if my adjacency matrix is also does also include the self loops, then when we multiply that with our hidden embedding, with our hidden activations, we will also gather information from the node's previous state as well, right? So we don't need to explicitly introduce the basically the step that we combined in this, right? So instead we can just construct a new graph that has self loops for every node in that graph, and we can represent those with just ones on the diagonal, right? So diagonal is representing the connections of the node with itself. If I add basically identity matrix to our adjacency matrix, that's going to construct a new modified adjacency. I'm going to show that with A bar. And now if I plug this A bar into our matrix form, I see that I'm taking the embedding for the current node into account, in addition to taking basically the other neighbors into account, right? So I don't need to have the explicit additional term that we had. We had here, right? So I'm basically getting rid of this term over here by modifying our A.
What would be the edge? Like, how would we, what would be the message passed? Some examples so that I can imagine.
So that's just a hidden activation that we have in the in the neural network, right? So you can think about it this way. You have basically your just a simple feed-forward neural network. You have X's, right?
Yeah.
And you're multiplying them by W's and applying sigmas, right, at each iteration,
Yeah.
right? But what's the output of this?
Oh, okay, so that's
It's
also,
hidden, right?
that's also a learnable path.
But not the activation. The W's are learnable, not the output. So output is just the input for the next layer.
Oh, okay, yeah, fine.
Yeah, so we have our basically initial, something that we have initially as our
Yeah,
inputs.
okay, got it, yeah.
So you can make an analogy with just feed-forward models that you have our initial features as input, but the difference is now that these basically also you need to take this adjacency matrix, the structure of the graph into account when you're doing this, right?
I was correlating, like in RNNs, we also have learnable hidden states, so I was thinking something like that. But okay, yeah.
Yeah, I'm really not familiar with RNNs, but or sequence models for that matter. So yeah, so basically you have that, and your output now here is just an embedding for different nodes, right?
I got it. Yeah.
So do we have new like graph neural networks or like this network where we have W for each age as different? Like here we are sharing the W with.
I mean, you can have everything. So you
Is it
can.
in practice or like it's just like, because you are saying like we have shared W, so it makes the job easier fast or something like, do people usually like they do have different W for different ages?
I personally have seen something. I mean, you can modify everything, but I have seen, the one basically cornerstone of these models is parameter sharing, right?
Yeah.
And it's very important. So the most idea that people use is to share these parameters across the network. Because it's kind of gonna be impractical if the graph is larger, right? But I don't know if, there's a particular method that for, small molecules, they have tried this, but I would say that that's gonna be impractical because you can't extend that to larger graphs, right?
Yeah, so like for molecule, like I was thinking like CO2, like double bonds was also different.
Yeah, I mean, maybe someone has done it, I mean, for a particular task, but that's still, when you develop some new model, you want it to be applicable, right, to other things, right? Usually models that are not, I mean, there are some models, for instance, in generative models, we will see that there are some approaches that are only applicable to graphs that have sizes smaller than 50, for instance. There are one-shot generators that are like that. So I'm not gonna ruling it out. I just haven't basically really worked with such a thing. So maybe there is, and maybe basically someone brings it up in the class. So, but that's basically the general scenario, and that's the goal that will help us to basically share these parameters. A question from our online folks. Okay, so let's just review what we have basically discussed today. We looked at a number of methods previously to construct node embeddings. Basically, we had kernel methods that were generating features, but then we moved forward to learning them using shallow embeddings. These shallow embeddings were essentially projecting our node indices into some basically low dimensional space. And by that, we were learning node embeddings for different nodes that we have. But there were some problems with that. They were not sharing parameters. That was one problem. They were transductive, meaning that we couldn't extend them to the future scenarios, basically that we haven't seen during training. And we weren't able to use essentially the features that we have on our model, right? So our graph. So in order to be able to incorporate these attributes into our problem, we wanted more sophisticated models like graph neural networks. And that's what we did. So the idea was that we wanted to define a propagation rule that was able to consume a graph and then return some node embeddings. And for that, we looked at a couple ideas that we can have. We looked at a feed-forward neural network. We looked at why we can't basically use that. That was because we wanted a model that is invariant permutations, and the way that we plugged our data, our graph data into such models was not accommodating that. The second approach that we looked at was convolutional neural networks. We basically wanted to define a window over graphs, and then we had a couple problems. We couldn't slide these basically windows over the graph, and we kind of didn't know if the number of nodes are changing in the window, how to deal with that. In order to address those, we used the idea of neural message passing. And by that, we looked at basically different nodes and their neighborhood. We gathered information from each neighborhood, and then we constructed messages that were given to each node, and we're updating those. So we basically defined a framework called update aggregate. We were taking basically aggregating information from the neighborhood as a message, and we were updating the current state of each node using that message. And we looked at a couple basically very simple models. We looked at aggregation as just a summation of the embeddings that we have. Then we looked at basically just linearly combining the our messages from neighborhoods with the current state of the node as plus some nonlinear layer as our update. Then we looked at essentially the computational graph of the flow of information essentially for each node. We realized that we can construct a subtree pattern for each node, rooted at each node, and we can show where the information for each node are coming from. And we realized that how we are sharing these model parameters when encoding information for each node. And then we'll basically discuss that starting, we can use our model basically embeddings of the graph as input, or we can, if we don't have any input, we can just construct something using the node importance algorithms that we basically measures that we discussed, like centralities, different centrality methods. And then we said that at the end of the day, after a few iterations, we are left with node embeddings that can be used for basically different tasks on the graph. And we looked at a simple model graph, basically a simple graph neural network that was linearly combining our information. And then we looked at some analogy on how this basically we can motivate the algorithm that we have using the isomorphism test that we discussed before. And lastly, we basically looked at how we can aggregate our formulation by introducing self-loops to our JSON matrix. That's it for today. I will see you guys next week.